Alright, here's our first video for Chapter 8, Chemical Equations and Reactions. So, as we're talking about chemical reactions, and the first thing we should talk about is physical reactions. So, with physical reactions, the big thing is that it is only a change in appearance. It's not changing what it is. It's the same material, the same substance. A great example of that is melting of ice. It's still H2O, it's just changed from a solid to a liquid. Chopping wood is another good example. It's still wood, you're just breaking it up into smaller pieces. A chemical reaction, though, is going to change the substance. It's going to create something new. So if you're looking at a reaction and something new has been formed, then you know it's a chemical reaction. Some examples of burning paper. After it's burnt, it is not the same material anymore. The black, ashy part, it looks different, it has a different texture, it doesn't hold together like the paper, it's powdery. It has all those different properties because it is a different substance. We put sodium in water. That was a nice explosion out of that. That's definitely a chemical reaction. The sodium reacted with the water, it produced hydrogen gas that ignited and gave us the explosion. We tested the water afterwards and saw that sodium hydroxide was created in the water, which made it a base, and we saw pH change out of that. It was definitely different than it was before. Another chemical reaction you can think of is eating food. As you go through the digestion process, it's breaking down your food, and when it comes out, it definitely looks different than when it went in. So it's definitely something different now. As we think of evidence for chemical reactions, color change is normally a really good indicator of a chemical reaction. Just like the burning of the paper, and we see color change happen there. Another good one is rust. As iron is rusting, we see that color change. We see texture change. It becomes brittle and flaky because it's iron 3 oxide now. It's an ionic compound, which we know has different properties than the malleable metal that the iron was before. When gases are produced, just like burning the paper, smoke comes off. Another reaction you can think of is this is zinc in hydrochloric acid. The zinc reacts with the HCl, the hydrochloric acid, and releases hydrogen gas, which is the bubbles that we see here. So that's something different, that's something new, that's definitely a chemical reaction. Forming of solids from two solutions. So when we think about a solution, we dissolve something in water. We talked about ionic compounds dissolving in water and how water pulls them apart. So table salt, sodium chloride. We have sodium and the chloride get pulled apart by the water, and when you dissolve salt in water, you get salt water. So it's still salt, it's still water, it's just a physical change. So if all that's happening is it's being dissolved, it's just a physical change. But if we have two solutions and we combine them, like this reaction here has lead 2 nitrate in the beaker, and then we're pouring some potassium iodide in there with it. They're both in solution, they're both dissolved. As the iodide ions meet up with the lead 2 ions, they lock together and water can't pull them apart. We would say they are insoluble now. And when that happens from two solutions, we make a solid out of it. We call that solid the precipitate. So this example here has a yellow precipitate. So we'll do quite a few reactions where we'll see precipitates formed. We'll use that as identifiers for certain elements that we're looking for when we're doing reactions. And there's a whole list of rules that we'll talk about that will help you figure out when things will be soluble in water or when they're not. Heat given off goes a lot of times with some chemical reactions, but it also can go along with physical reactions. So we could have a physical reaction like doing this. You warm up your hands. I'm not changing my skin. It's still skin. It's still the same material, but the friction there created heat. So as you think about what's the source of that energy and heat, it can be going along with chemical reactions. It can also be endothermic. We talked about that too, where it's absorbing energy, so it feels colder. With light given off, like burning the paper, we see light coming off from chemical reactions sometimes. Also, you could think of like a light bulb with the electricity going through the light bulb. The electrons flowing as they go through the tungsten. There's resistance from the tungsten of giving up electrons, and that kind of creates friction there and creates the light that we see from a light bulb, even though that's just a physical reaction. When we're writing chemical equations, there's symbols that we're going to be using, and for the states of matter, as we show them, like with the iron rusting, well, the iron is a solid, so we would put a little s in parentheses down as a subscript down below the chemical that you're talking about. That is a solid. For a liquid, I didn't have the right font here, but normally we don't use the lowercase l like that because it looks like a 1. You'd use like a cursive L. So I'll be writing some here soon. I'll show you the cursive L. Gas is going to be a little g with the parentheses again. And then when we dissolve something in water, we call it aqueous. So just like aquarium and aquatic and Aquarius, all those things deal with water. When something's dissolved in water, it's aqueous. So when we put the salt in the water, it was aqueous. It wasn't liquid salt. You had to be a couple thousand degrees to melt salt. And then it would be liquid. So aqueous is just dissolved in water. Now, as we show, the things that we start a reaction with are called the reactants, and then we use an arrow to represent that a chemical reaction has taken place, or some kind of reaction. Maybe you can do this with physical too. So the arrow represents that a reaction has taken place, and it gives you direction. Now, you can also have a double arrow, which means it's a reversible reaction. The reaction could go back the other direction. And so those are kind of special things there, but that can happen too. Now, there's also some symbols we will put above the arrow sometimes. The triangle is our delta, and that means a change in energy. We could put heat on there, which kind of is the same thing, possibly. Or you could have a temperature written on there, and that would be that reaction requires a specific temperature for it to take place. With some examples of this, as let me get rid of that. As we were writing out these chemical reactions and doing an example of H2O. So if we have H2O and it's a liquid, so I'm going to use my little cursive L there with parentheses around it. And now if we add some energy to this in the form of electricity, we can have this break down, and we can break down the water into hydrogen gas. And remember our 7 elements that are diatomic. Hydrogen is diatomic, so it would be H2, but then I would put my little G down here to show that it's a gas. And it's also going to make oxygen, which is another diatomic molecule, and it would be O2 with the little g showing that it's a gas. Now, you may notice that, hey, what's going on here? We're starting with 2 hydrogens and 1 oxygen, and somehow we got 2 oxygens out of it. We'll talk about balancing these equations where we do make sure the ratios of what we start with. These are our reactants. And these are the products. So reactants are what you start the reaction with, products are what you end the reaction with. And we will talk about the balancing where we make the ratios of the elements equal to each other, so nothing's popping out of thin air or something like that. I brought up rust, so let's see that one. We got iron, and iron is a solid, and it's going to react with oxygen gas. So O2 again, since it's diatomic. And we are going to make iron 3 oxide, which the formula, we would take this and Fe2O3, and rust is going to be a solid. The one that I showed you that made a precipitate, we had 2 solutions. We had lead 2, so it has a positive 2 charge. Nitrate has a -1 charge, so we need 2 of those. But this was dissolved in water, so I would show that as aqueous. And that was reacting with potassium iodide. And that is also aqueous. Now, we combine those 2 aqueous solutions, and we think of mixing the parts. Positive, negative combinations, right? We could combine the potassium with the nitrate. Now, like I said, there are rules, and you'll be able to go through these. A couple simple rules that you can remember is nitrates are always soluble. It doesn't matter what nitrate's with. Something nitrate is going to be dissolved in water. Water can always pull it apart. The other one is easy to remember is the alkali metals are always soluble, except lithium fluoride. So potassium is always soluble. So this is definitely, the potassium nitrate is definitely going to be aqueous. So since we know it made a precipitate, you can rule out the potassium nitrate, and our lead 2 iodide must be our precipitate. It is not aqueous anymore. Water can't pull it apart, so it is a solid. Again, I'm not balancing this. We can see that there's 2 iodides in the end and only 1 in the beginning, so we'll talk about the balancing of it. But these are the correct formulas. We've done the charges and made the formulas done correctly. Last one I'll show you is ammonia. So NH3 is ammonia. It is going to be a gas. It dissolves in water readily, so we can put those 2 together, put water with it, H2O, and again, that's a liquid. I'll use that cursive L. Now, this is one of these ones that has a double arrow, and it can go both directions like that. So it's going to make ammonium hydroxide. So as we look at that, and that is aqueous. That's dissolved in water. So this is, when we talk about acids and bases, we'll find out that this is a weak base. But when you think about both parts here are going on, there's the ammonium hydroxide, and then it gets pulled back into ammonia and water. And so it's constantly kind of going back and forth with those. So that's the basics of setting up chemical equations and talking about chemical reactions. We'll talk about balancing equations and show how we have to keep everything with our reactants and products the same. So get working on that homework.